So we have gone through equation of motion in this past week, and we had a worksheet of applying that equation to a specific problem in CouetteFlow, which is where I have two coaxial cylinders and the other one is rotating. And this is how viscosity cylinders work. And you have gone through the motions of putting it together. Now, here's the question I have for you. Shell balance, or balance over a small shell of a liquid, and then figuring out an equation that I get after that balance. In equation of motion, essentially they work because they're based on the same principles, right? Conserving something over a small shell volume. However, in terms of solving problems, they feel different. Which questions do you have? Do you see the parallels between the two? What are the biggest problems you have in solving the problem? But in this last worksheet, I asked you to complete it. Started in class. What wasn't clear?
I feel like this worksheet I liked it because you gave us like the VZ is equal, or like assuming that the VZ is equal to 0. But then like when I do problems, sometimes I don't know when to make those assumptions. Like when we did the thin film that was going down that ramp, we assumed that the pressure was like 0 or something like that.
Yes, so basically we assumed no acceleration down the ramp, so that you actually have this. So my VZ, or whatever is parallel to the ramp, those velocities were going in a sort of parallel layers, and each layer had a different velocity, but velocity within the layer was constant. So I had just dependence on the distance from that ramp, and that was it. Then I had a constant velocity and a constant distance from the ramp. Normally, and then you can do like, that range wasn't like this. If it was like this, I would obviously have acceleration. I wouldn't be necessarily able to assume that, but the ramp was almost parallel to the ground. In those cases, you can do that. It's a little, so we are learning the process. Part of it is like in assuming what is 0, what is not 0, comes from practice or even knowing what it does in the lab, which we don't have a lab. And doing this part of the lab would be, because you would have to experimentally figure out how things are going, and you would have to solve the equations at the same time in one specific course. Let's say that it would be a challenge. So yes, part of it is figuring out what to assume and how to assume is difficult. In this case, though, so thin film is one case. Most other, where it's a little tricky, I'd say. All of the assumptions that we are lining up, they're a little tricky to know beforehand. But once I lay them out, we will understand them. So for thin films, generally those will be assumptions. What could change is boundary conditions. So, and what is so, technically I could also move that plate under the thin film. So my boundary condition for velocity will change. Right? I could have some shearing with a different fluid. That would change the boundary condition, the shear stress on the boundary. So now there's this variance, and boundary conditions do influence solutions a lot. So I had a question before that.
Yeah.
Keep going on.
I got that answered, but then I just had another one. So if you're moving the plate, wouldn't that only affect it if it was a non-slip?
Yes, so no slip refers to the relative slip between the fluid and the plate or solid. So even if the solid is moving, and I'm assuming that my fluid has that same velocity, that's still no slip. There's no relative slip between them. So you could have moving machine involved all the time. So those are very real problems in the movie. Right? So I could kind of, and there was one example in homework where there was a cylinder moving, horizontal set, and there was an inner cylinder moving. Variations of that. You can see where this is going. You can move all of the solid surfaces separately or together. Or, yeah. So it's still no slip. And just most of the time you will have non-moving solid surfaces, and that means that the velocity on the boundary is zero. But technically, it's no. The fluid and solid are doing things. There are cohesive forces that are moving that first layer of fluid along with the solid. That's it. That's our assumption. And so it is moving because, well, it's easier to. I mean, I check where I want to go. There's something outside of the system that is moving. So there's multiple layers here. There's setting up the equation. I could do that with shell balances, or I would just apply the equation of motion. In that sense, we have technically worked with the equation of motion all along. We just kind of, when we do shell balance, we immediately assume certain things are non-existent, and we just go with that. Whereas when I open up, I have that slide. When I open up the shell equation, the equation of motion, this is for cylindrical coordinates. That is true for everything. Then I'm just killing the terms based on my expressions. So those are just two approaches for the same thing. These are shell balances. They just also have a time component. So balancing in time as well. So equation of continuity and equation of motion, both of them are based on conservation of quantities. And shell balance is based on conservation. Okay? It's just, it is a lot. When you see something like this, you're like, the first reaction is to freeze. But just don't freeze, breathe, and then see what to remove. Now, for your assignment for today, if you have trouble looking at the, what I call, this is R, theta, and Z balance. I have momentum, I have R, theta, and Z momentum, if I'm in cylindrical coordinate system, or if I have a Cartesian coordinate system, I have X, Y, and Z momentum. Either way, it's a vector, right? So I have three components, however I decide to look at those components. Now, when we looked initially at theta, because my theta cylinder was moving in theta direction and had a constant angular velocity. So that dictated that I first look at the theta momentum balance. And theta equation here is this B65. That will then give me that velocity in theta direction when I solve it. Now, if I don't want to look at theta, I can actually look at others. So what did you get when you balanced this R equation? Did you get anything? Or was it clear? Or negative? I don't have it in slides. Okay. I say this. Negative rho v theta square over r is equal to negative dpdr. You got that? So now from theta equation you have v theta. So you can see how pressure changes with radial direction. So I have some response in pressure from this movement of the plate. I actually have some response in the pressure. This is these very nonlinear responses that are happening because my momentum can kind of transfer across all of the coordinate planes. And in 3D, that can be complicated. And then I do have some gravity, so this is some gravity influence if I want to look at that. Though technically we have ignored that. So this is one part we said that the gravity influences are small. So one would, for instance, could say now as a further simplification, I'm going to ignore this pressure in Z. And I'm going to say that that's approximately 0, and my dominant pressure disturbance is from this movement of the plate, which is in that direction. And then I would solve for pressure as a function of R. How did I even get there? Well, first I already assumed that Vz is equal to 0, or assuming that it's 0. That kind of kills me looking at changes in the direction. So technically that would then inform me to kind of ignore these as well. But formally, really, pressure is a function of R and Z. And solving this together, right? So there's a linear change with Z, and then there's this pretty nonlinear change with R. Right? So solving that together can be problematic. I can simplify it by assuming, because now it's a partial differential equation. Oh, we're solving ordinary differential equations, right? So I could assume, well, this is relatively small. I'm going to ignore that contribution and then actually look at this. But I didn't ask you to solve for pressure. And most of the time, we will kind of stop at velocity distribution. I will tell you, I want velocity or I want pressure. But technically, we need it all. So we have 3 components of velocity and pressure as a field. Right? So those are 4 components that can depend on 3 different coordinate components, right? And time. In reality, though time we typically kill by steady state. So we wait for things to stabilize. So this was okay to just get from the. Now, do you realize how you would actually, we actually did, as an example, shell balance and cylindrical coordinate system already. It's just that we focused on Z momentum balance because our velocity was in Z direction, and we just had this driven by pressure. So there we know, basically, if you wanted to solve that problem, you would start from Z momentum first. Or in the shell balance, balance in Z momentum, I could solve this problem by the theta momentum first. Okay.
On the test, shell or
I would be probably very specific. If I'm not specific, you can do it. But to simplify my life grading and your life what you lose, I don't like it. But that's part of also testing of this first test. In real life in general, nobody will tell you do precisely this. You're developing certain set of tools that you have to figure out how to apply them, right? But here I want to now this first test I will want to test, do you know how to do shell balance? And then I will directly tell you do shell balance. Part of it is like, do you know the mechanics of how do you go through the motion? In terms of solving differential equations, is that okay? There's a little bit of friction that I noticed when integrating, where was it? Was it this one? You have something like this. Thoughts on you? Is it clear now how to integrate? Always go layer by layer. So I have this, especially if I have derivative with respect to whatever, in this case R, of something that in this case is a function of R, however complicated it looks like, it's a function of R. We assume that V theta is a function of R. So this might look scary, but it's just some function of R. If derivative with respect to R of a function of R is equal to 0, it's same as saying f prime of R is equal to 0. F of R has to then be a constant. So again, take a deep breath, okay, and ask yourself, what is this function of? And typically they're simplifying things so that I can depend only on one coordinate. And I have one coordinate velocity that is non-zero. So in the case of the Couette cylinder, I have things are moving for the most part because there's this major piece of equipment on the outside rotating. And that's dictating theta momentum. So I'm assuming that only v theta, velocity in that direction, is non-zero. Everything else is small enough that I can neglect. Right? So my v and vr are zero because there's nothing driving the fluid in that direction. That's my starting assumption. So I have one velocity that is non-zero, v theta here. When we have things falling down because of either pressure gradient or gravity imposed, then it's my z velocity that is non-zero, and I orient my z down on a cylinder. Right? Whatever, however cylinder is inclined, orient z down that cylinder. So then my z is non-zero. All other components, there's nothing driving things in radial direction, so VR is zero. And same for v theta because there's nothing rotating. So in that case, I have the non-zero survivor is VC. Right? And then that non-zero survivor, for you to be able to solve things analytically, technically has to depend on only one other coordinate. It's the lyrical system that's typically in the radial one. So basically, you simplify you make assumptions so that you simplify it to one non-zero velocity depending on one other coordinate. So then you actually can solve these, at least for a velocity distribution. For pressure, as we said, as we saw, these were not ordinary differential equations. But I could simplify further and say, well, since I started ignoring gravity components in the direction because this is short distance, and it's probably not very large, then I could ignore my pressure disturbances. Okay. Any other questions? So we are cool with simplifying v theta and applying boundary conditions to get v theta. Then you're cool with simplifying R equation and Z equation. And then I was asking, what is the force exerted by the fluid on the outer cylinder? And where I stopped the video, in part because I decided that it's better discussed in class, where I stopped the video is just looking at the force exerted just on one area element. Did everybody get that part, and are there questions about it? So first things first, the way we look at the shear stresses. Shear stress is force per area. So shear stress I can imagine as basically force acting on one little area element in my coordinate system. So that means that it's per area because that area element has normalized area. So and to get the total force, I will always kind of multiply shear stress on that area element times the area of the element. So my shear stress, by definition, when I look at R and theta or any Ij, right? In this case, it's a force in theta direction exerted by the fluid in sort of like lower R direction on that fluid that is in the higher R direction. So here, beautiful large cylinder. Okay? Now, let's say, so here I have fluid that is on the inside. Relatively to this cylinder surface, the coordinate system where R starts from the middle of the cylinder, okay? That coordinate system, my fluid in this bottle is in the lower R area, correct? And my solid that fluid is exerting shear stresses on, okay, is relatively to the fluid in the larger area. So basically, I I'm looking in the coordinate direction when I'm looking for the fluid to the solid. So if I was looking at the force that fluid is exerting on the solid, it's essentially aligned with the way I'm looking at the shear stress definition. Now, this is just a definition in a specific coordinate system. When I evaluate tau r theta by all the formulas that I have in appendix, I get a force that I assume is exerting by something that is in the lower R on that is in the larger R. So in this case, I would take that tau r theta for every element. I would take that tau r theta from the middle, okay, and just multiply it by the area element to get the force. However, if my fluid was on the outside here, okay, so I could have, I don't know, fluid film, I could drop it and let it slide down this, okay? Then, when I apply formulas to calculate tau r theta, they're tied to the coordinate system. And if my coordinate system starts from the middle of the cylinder here, then technically, fluid is on the outside, or my larger R relatively to the solid. And if I'm wondering physically, what is this fluid exerting on the solid, I'm going to have to take minus tau r theta. Just to get how things are oriented. The only difference is plus minus, so the only mistake, if you make a mistake, is that of direction. Okay. Now, if I have coaxial cylinders like here, okay, so if I'm asking what is fluid that is in this area or this area, okay, exerting on the outer surface in terms of a force, then on every little patch here, area element on the outer cylinder, I will just take tau r theta because the fluid is in the lower R and my solid is the higher R with respect to the fluid. So basically my tau r theta is giving me the correct direction. So basically my force exerted on the outer cylinder, fluid onto the cylinder, right, is tau r theta times the area element, or area of the element. Yes? If I'm on the inner cylinder here, this fluid is on the outside of it. What that means is actually in the region of higher R values, not lower. Okay? So to actually evaluate physical force that fluid here exerts on this solid surface, I have to take minus tau r theta evaluated on this inner cylinder. So for R is equal to kappa R. Do we see that? So the way shear stresses, especially in the formulas, they're sticking to the coordinate system. Coordinate system doesn't know where your fluid is. Doesn't. So the outside or the inside, this direction, that direction, this is just the coordinate system. So these formulas relative to that coordinate system. And sometimes that's going to be plus or minus because coordinate systems, they always have a sense of very defined sense of direction. And they're defined relative to coordinate vectors in that coordinate system. But those are arbitrary, right? But they're stuck. Once you choose it, you're stuck there. So if I'm asking you what is fluid, what is the force fluid exerting on a solid surface, I have to figure out is the direction of fluid to solid, because that's what I'm aligned with the coordinate system over against it. That's all. If it's against it, I'm going to have to take just the negative value of what coordinate. Again, tau r theta is tau r theta in the general fluid, especially if you don't have solid surfaces. And it's just telling you by convention, they're looking at tau r theta as a force exerted by the lower R values of fluid to the higher R values of fluid. whoever is flowing and how, whoever the system doesn't care. Yes? So this is where I asked you for your practice. And so suggested practice for the exam are problems here, especially the cylindrical coordinates. Because that's what you're focusing on right now. Can you figure out whether you can, well, so first cover this side, okay, where the answers are, and see whether you get the correct answer. So answers are given. But this is where plus minus will tell you whether you understand what I just said. So this is, we're asking about figure 122. Okay. Cover the answers and see whether we understand what I just explained in terms of the shear forces.
To the slide where you're deriving tau r theta.
Okay, so let's actually now look at this. So now I just defined it. So my tau r theta evaluated of this outer cylinder is the force on this r is equal to r solid surface, which is sitting in the outer region with respect to the fluid. So if I want to evaluate it, I need what is my tau r theta equal to in terms of velocities. And for that, I go to B, and that's in these. Where did this go? It's in this book, but if I pick it up, it's part already. I wasn't there. So I started copying things. So my B1 tells me how to evaluate shear stresses. And again, these are the most general formulas. You care about the Cartesian and cylindrical coordinate system for now, because we discussed spherical. Technically, spherical works the same way. Practically, it takes a little practice to work those formulas through.
Derivative in respect to r in the second to last line, I think, or go down the second to last, yeah. The constant omega.
So this is a constant here, so I just didn't have it. It's a zero.
But you should still factor it out for that term because it multiplies to it, right?
It multiplies 1.
And to the negative kappa r.
Oh, so I missed omega 0.
Yeah.
Yes, I did. Apologies. There's an omega 0, 1 minus k, but I didn't actually solve this, so I didn't catch my mistake. So what did you get this tau r theta? Let's actually grab. So I'll give you right now what it should be. So you should get the tau r theta. But what did you get? But so you got, oh, no. So you got tau r theta. Of r is equal to
Smaller squared and times that constant.
That was omega 0 over 1 minus kappa squared. So this is an expression of R, and I can here, for the shadow, I can evaluate it with respect to R. Now what I want to point out, what I stopped myself, let me just see, I guess my notes should be somewhere here, close by. Oh, there we go. Yes. Yes. Minus 2 mu omega 0 kappa square r square over r square. Yes. All right. So is everybody okay with this portion? That this is force, including its direction. So it's a shear force, so it's directed on the cylinder. The shear force works in this direction. That's a theta direction. That's also how fluid is moving. So my force at every point here, it depends on the theta I'm taking. So at every point as I move around, it's going to change direction. Its value depends only on R. Yes? So if I look at small little elements around, the value is constant in terms of R, but it's changing the direction. So my theta vector changes the direction. If I wanted to integrate this just to get the total force, my question was what is the force? So it was a little not straight. It's saying what force do I want you to calculate? So this is force per area element. Okay? Now, if I actually wanted to integrate all of this sharing that is going on, how would I do that? What am I integrating? And this is the part where you might or might not remember how to integrate over a surface. This is multivariate calculus integration on a curved surface. Double integral. So I'm going to write it in surface of cylinder. R is equal to R. Right? Of this force. So I'm going to call this F R theta, and it's a vector. Okay? And that vector is actually, so my value depends on this evaluated at R and theta, because the direction of the vector depends on theta. So if I evaluate all of that, this is actually, so surface of the cylinder is described by going from 0 to L in z direction, so it's a double integral, 0 to 2p in theta direction, right? This is this value. I'm just going to write it as tau r theta evaluated at R times, and then area times this vector that technically depends on theta. And I'm going to write that because it depends on where I'm at. And then area element. So normally, if I was in XYZ coordinate system and I had a coordinate vector with respect to X, Y, or Z direction in Cartesian coordinate system, I could just put them outside of the bounds of integration because they don't change. They're constant, right? However, theta coordinate vector in cylindrical coordinate system, it changes. So again, what I'm doing now in the next derivation, I'm just putting your calculus to use, that's all. Okay? So if the review is a little painful, well, it is. So this changes. So in order to integrate, I need to know how does it change with respect to theta in order for me to actually properly integrate. Is everybody seeing that? I cannot just pull it outside the way I would normally want to do with the coordinate vector. I can do that in the Cartesian coordinate system. I can't do that if this thing changes. I could do it with delta z. Z coordinate vector doesn't change depending on location, so it's a constant, but this one is not. It changes direction. We need to actually express this vector in terms of some coordinate vector, some constant vector, in order to do this properly. So I actually need to go and look up, and one coordinate system that doesn't change is Cartesian. So the best way, so this is a constant value, as well as this, right? So those two things I can pull outside of the integration. But what I'm left here, slide, okay? But what I'm left here with, in terms of integration, just like total force, is that my total, I'm going to call it F total. Just the force. On that outer cylinder, is tau r theta of r times r. And then integral from 0 to L, integral from 0 to B. And again, it's a function of theta, d theta, dz. Now, I can actually look this up in appendix. And I have it written down, but I don't know where in appendix, but it's somewhere here. So I'm going to tell you right now. In these tables, I believe that I did put cylindrical coordinates. So basically the A6, 11, there's cylindrical coordinates, delta r, delta theta, delta z, expressed in terms of Cartesian. This is equal to minus sine theta delta x plus cosine theta delta y. And this is a neat trick because it gives me actually what function of theta is this delta theta. So I can integrate. And these are constant in space. Constant. Okay. So what this integral is, and I don't know why did it decide to do this, but okay. This integral here is, it's actually integral 0 to L, 0 to 2 pi. I'm going to now pull out constant minus delta x of sine theta d theta dz. That's from this first term. And then plus delta y, 0 to L, 0 to 2 pi, cosine theta d theta dz. Now I can integrate. I have a function of theta that I integrate with respect to theta. What is this? Say it's cosine. How will I evaluate it? I'm going to have cosine on 2 pi minus cosine of 0. What's that? Same thing. So it's a 0. Whether I thought it's a cosine or minus cosine doesn't really matter. In this case, it's going to cancel. But that said, you should look it up, and yes, it's useful to have on your cheat sheet or something. Same thing here. It's going to be sine theta or cosine theta. Sine theta or minus sine theta now, I don't know. But it's going to cancel. So this is a 0, this is a 0. So this total force evaluates to actually 0. For this shear force. What doesn't evaluate to 0 is the torque, or the tendency of the force to rotate an object. Okay? So that we need a different physical. So that's kind of a little surprising, but what doesn't evaluate to 0 is torque. And that is moment of force that tends to rotate an object, because we have a rotation here. So if you had sort of an arm of the force with, I'm going to overuse R here, R, and then there's some force F. Right? The torque is given as cross product of that arm and F. Right? So what would be the total torque on the outer cylinder? What is this arm R to the outer cylinder as a vector? That's the value, and the direction is delta R. Okay? So it would be basically on a surface element, I would have to integrate. So I'm going to put the double integral of R delta R cross product my force, and that's tau R theta of R. And why did you do that? Of R delta theta times R d theta dz. This was my force. Well, this entire thing is a force because this is the diameter. So I take my arm to the cylinder, right, at every point. And now I have a new, so this is a constant, this is a constant, this is a constant, we're good on that. I have to figure out what is the cross product of R coordinate vector and a theta coordinate vector. Oops, I need somebody's arm. This is R and this is theta. And they change as I go around the cylinder, right? They're always orthogonal. Do we remember cross product? So what's going to be the cross product? In which direction is the cross product going? Z direction. Well, this is a positive coordinate system that we choose, so it's going to be delta Z. That's how we actually set coordinate system. Cross product of the two coordinate vectors in a right-hand sided coordinate system will be the theta. Okay. Did I say that this was going to be a revision of your calculus? Yes? All right, well, this is where it's used. So this is delta Z. So that's a constant vector. I can pull it out of the integration. So I can just integrate, really it's just an area. So the cross product, now, did I? Yes. So I'm going to change the color here. Delta theta is delta Z. Cross product. So this is great. And this is a constant vector. Vector can pull outside. So my torque will be in Z direction. And this integrates, this is just the tau r theta, which we already have, times r squared, times integral, double integral over d theta dz, so that's times p times L. Area of the cylinder. Well, area of the cylinder I have with r squared. With r. I'm going to leave it on this same slide, or do you want me a new slide? How messy is this to read when you look at the notes? Should I leave it on the same slide? Do another one. Will do. So just give me one moment to write it down, and then I'm going to move to office hours. So basically, then my total torque outer cylinder is r squared tau r theta of r delta z 0 L 0 to 2p d theta dz, and this is 2p times L. So you get 4p mu omega 0 r squared L kappa squared over minus 1 kappa squared delta z. And it's that magnitude, the reason why I wanted to drag you through this exercise, because this is where calculus is actually useful. It's that magnitude that we know for the system that is rotating. So without going into the details, if I'm doing the viscosimeter, I know what this torque is simply from my equipment, and I can measure it independently, regardless of the fluid that is inside. So my omega 0 that I'm rotating with is known. R, L are physical, these are kappa, those are physical parameters of the geometry. If I don't know mu, by equating this to the torque, then I calibrate it from the outside using my solid portion of the equipment that I'm moving things with, I can recover what mu is. So this is how viscosimeters work.
What's the
One minus kappa squared. That's the K kappa. from the unitary cylinder. Yes, I'm apparently missing a minus. Yes, there was a negative here, so there should be a negative here. So this is known from rotating equipment. So I can find mu. So I can go find effective viscosity of this fluid. If the fluid is Newtonian, then it's constant. If the fluid is non-Newtonian, I'm finding effective viscosity. Yeah. Okay, so I need those sheets, or rather, Min needs your sheets. And